My name is Frances Newcomb. I'm a new member to relatively since October of the League of Women Voters, and I've invited Evan Timar here. He is the public utility manager for the city of Moscow. He oversees both water and sewer operations and has worked in the utility sector for over 10 years. He became manager over Reclamation Division in 2019. So I'm just going to let Evan take it away.
Awesome. Hello, thanks for joining me on this nice spring day. I didn't even realize spring just hit us. We're out of winter officially, right? But I definitely have the honor of speaking with you guys. I wanted to talk about the reclamation facility that we have and kind of our interagency agreement with the University of Idaho on how we recycle that water throughout this process. And so, a little bit about me. I got into the utility industry when I was going to college. I became fascinated. I was taking night classes in the wastewater side of things, and I became fascinated with these treatment facilities. They essentially do what Mother Nature does, but on steroids. They do it in a 24-hour period, and it's really a fascinating process. And so what I'll be doing, I'll walk through the history of the facility and then talk a little bit about the general processes that we have at our current facility. And then I'll jump into, towards the end, the way in which we recycle that water with the University of Idaho. Before it gets to the actual facility, we have a collection system that everybody's well aware of. We have sewer pipes out under the ground, and we have about 89 miles of sewer pipe that we own and maintain. Residents, if it's going to a property or a building, that sewer pipe that goes and leaves the sewer main is the ownership of the property owner. So we have roughly 40 miles or so of that. We have 89 miles of pipe. We have 40% of the system is clay, and that's relatively in the heart of the community. Yeah.
Evan, could you use the microphone?
Oh, yeah, absolutely.
Please. Thank you.
I didn't even test that, so let's testing.
Yeah.
Testing.
That's great. Thank you.
Yeah, thank you. So roughly 40% of the sewer system that's out in the city is clay, and that is more so in the heart of the community. We actually have physical contract from 1890 of some of the first installation of the clay system, which is really neat. And as it starts expanding outwards, you get some of the concrete sewer pipes that we have, and then really since the 70s, we've started installing PVC, polyvinyl chloride pipes, the plastic, and those are roughly a 100-year lifespan on those pipes. But the clay that we do have has held up really well in portions of the system. And we have a variety of size, anywhere from 4-inch that's in our system up to 36-inch, and those 36-inch pipes start creeping more in this direction as they approach our reclamation facility, which is right here. We also have 4 lift stations. Generally, when they're trying to think about a city and how they're going to get sewage to dispose in a direction, they're thinking of the lowest point, and so just kind of follow the creek line and set it there as it leaves your city. So that's just to be advantageous and get the gravity system rather than pumping, which we do have these 4 stations. One of them's down here, the South Lift Station. It's our largest one. And that pumps up a gravity line to get up to here, and then gravity's through. We have Orchard lift station over here, the Southeast, which is in our Southeast Sewer District, and then we have our Mall lift station. Soon to be 2 additional lift stations, one in the Eddington subdivision, which is down this direction, just west of SEL, and then we'll also have another one up at the Logos, the new Logos site. We'll have another lift station. So we'll have 6 lift stations in the system, which pump the sewage from a low portion and get it into a gravity zone to further bring it along to our reclamation facility.
What do those look like?
Yeah, the lift stations consist of a large wet well where the sewage can then collect into, and then depending on their size based off of a kind of a maximum peak day demand. So what could the station potentially see over the next 40 years or so? And they just have a rail system and pumps set down in the bottom of them. and then a valve vault to manipulate kind of where you want that sewage to go, and a bypassing system. So they're typically like a footprint about the size of this building or this room here, and then just a large wet well to hold roughly 15 to 20,000 gallons of sewage.
I've noticed any of them.
So some history on the facility. The first facility was built in 1918. It didn't consist of much. It was some septic beds, septic tanks, and some drying beds. And we also have that original specification document from 1918, which is really neat. And the only thing that those were kind of located in this region. And so in this photo, you can't see those septic beds, but the facility since then has gone through 4 major upgrades. And in 1938 was probably the most significant, the first real significant upgrade, which was these trickling filters. They're about 100 feet in diameter, and they consisted of a media, so a porous media, typically just stone, a rock, and it would allow that wastewater to go over these distributors and then just kind of filter out on top of this media and go through. And the media grows what's called a zooglobal mass, which essentially helps remove the nutrients from the wastewater. They're not highly effective, but there are still trickling filters to this day throughout America. And actually, Coeur d'Alene has 2 of them, and that's what they use to remove their nutrients. But it's on a plastic media rather than a rock. This photo was taken roughly in the late 50s. I don't know the exact year. We still have this tank. This is our primary clarifier, and this tank out at our current reclamation facility. But from 38 to 73, there was a variety of upgrades: the digestion system, the contact chamber system, and the clarifier in 1956. And so it went through a lot of upgrades, but not really until the late 70s did things start really advancing pretty rapidly due to the Clean Water Act. So once the Clean Water Act hit, that obviously the EPA had to start looking at what do we really need to prevent from hitting our waterways. There's tons of the research on things takes quite a while to do. They look at river bodies, they look at small streams, they do what's called a TMDL, a total maximum daily load on these bodies of water to see what would be impacted by a certain nutrient level or a potential contaminant. As they keep researching things, there's exotic contaminants. It's almost never ending what they're able to find in the water. So the more they learn, the more advanced these treatment processes have to get. And so it's just an ever evolving process for us to keep up with infrastructure upgrades. So the next phase after 73, there was really nothing until 1996, where we upgraded a dewatering process and a chlorination system. We put in a building. I'll dive into the dewatering process a little later, but you're taking the built up sludge that, yeah.
Evan, I just have a quick question.
Yeah.
Would you rather people ask questions while you're talking, or do you want to wait until the end?
I'm fine making it a conversation if people want to ask during this. I leave time for questions, so I'm fine with that.
Okay, thank you, sir.
So the dewatering process was introduced, and the chlorination system, that's a chlorine gas system that we'll jump into. And then in 1998, we put on a new headworks building, which these are old auger monsters. The headworks is the first initial defense of the treatment system. During this time frame, in 1997, the EPA started going over what our permit would start to look like, and so they started doing their TMDL, studying the creek, what would be impacted if we didn't remove X contaminant in the water. And so in 1999, after we completed this, they issued us a permit, and that is still our permit to today. It was issued in '99. It expired in 2004, and it's been administratively extended since 2004. And so the EPA issued these permits. I don't want to bore you with all of these numbers, but there is a really important parameter that we do look at, which is total phosphorus. It's one of those It's one of those nutrients that causes, it's the most rapid producer of eutrophication, just, excessive growth in a body of water. So aquatic life gets impacted because you have plants trying to grow, because it acts as a fertilizer in a body of water. And so you reduce the dissolved oxygen concentration in whatever that receiving body of water is, and then it impacts freshwater biota. So that's a really important one. It is the trickiest nutrient for us to remove. It takes a lot of internal manipulation of our process to help and make sure that we achieve the parameter that they've given us, which is 0.136 milligrams per liter. That doesn't mean a whole lot, but to most people, but it's a really small amount of this contaminant that we're able to have leave the facility on a daily basis.
Would it help for people to reduce their use of
that's a great
fertilizers?
question. Well, so it's not so much that we get runoff, but that does have some mild impact. But it's in a variety of household products, and so there's not much we can really do until stuff like that's banned. They created these processes to remove them and remove them very effectively, but it's costly, and just like any contaminant that we're going to try to remove, it definitely takes a lot of energy to do it. That's a great question, though. So they issued this permit to us, and we've had that one since 1999. The Department of Environmental Quality has taken over primacy. I think during the Trump era, they defunded the EPA a little bit, and so they had to drop that oversight over to the states because they just didn't have the staff to oversee those anymore. So we now deal with the state of Idaho through the Department of Environmental Quality. They are working on our new permit, and they're anticipated to start that in June. Yeah.
How's the legislature's funding of DEQ now?
I am honestly not sure, but I do know that they are hiring people actively to help address some of these concerns because they initially had very limited staff to take on some of these new programs that they were faced with. So another one being biosolids, which is really tricky to tackle. So there's one guy for the whole state. Yeah.
So you've got about over 1,000 pounds of stuff to get rid of every day. Where does it go?
Yeah, so it stays. It's a great question. So depending on what it is, it stays with the microorganism. So that's a fantastic question, and I'll get into that and how that kind of works. But ultimately, it is disposed of in a biosolid content, and it becomes compost. So it's really neat. So the facility, the final two real upgrades, just from an overview standpoint, were completed in 2002. When we got issued the new permit in 1999, we had some trouble. We knew we were going to have trouble meeting that permit with our previous facility. So we knew we needed to do something. We had went out for bond on getting a funding mechanism in place to install this aeration basin, some pumps, secondary clarification, and then later on in 2010, a tertiary filtration system. And this is really the heart of the entire treatment process, removing these components out of and meeting the parameters that we need to meet in our permit is done purely biologically. It is a biological function where we have microorganisms really doing the bulk of the work to remove the contaminants in the water. And so just to give you a general overview, this is east, and so we got north going this direction. The water flow path is coming through this headworks area, making its way down here, hitting these pumps, flowing through this process, and then going this direction, and ultimately out to Paradise Creek. So just as we start walking through this briefly, that's kind of the flow path that we will be taking. To start with, we have, just to give you guys some general treatment figures that we're looking at, we see about, on average, somewhere around 700 million gallons of water come into the facility. So that's looking somewhere around 2 million gallons on an average day that we have go through. What we do experience from time to time, the collection system, all the sewer pipes out in the city aren't necessarily sealed tight. And so the older stuff that we do have, especially when they laid it in the early 1900s, they allow it to weep. We didn't have a mechanical means of cleaning the sewer pipe, and so they didn't really have gasketed joints on everything. And so these sewer pipes are just 3-foot joints going down a sewer line. And so they allowed it to weep to be able to self-clean. We didn't really have a mechanism of getting in a 6-inch pipe and cleaning it really well. And so when we do see the ground get super saturated, especially during the shoulder seasons, we will see increased spikes of flow come in. That's not necessarily because we're attached to the stormwater system. We do have separate systems, but we will see an increase in the ground saturation, and then that will come into the facility. That is, it's from a daily perspective, it's very rare to happen, but we have had, we do have events where we see surges in the water. That's incredibly common across the country. Yeah.
Is that in the older parts of the city where the what do you call them, the sewer things would come off and the water would be spraying out?
Well, yeah, so
Is
during,
that it?
I know the downtown area, the stormwater system has trouble, kind of handling that, and so we do see a manhole just surging with water coming out of that. That's primarily the stormwater system. The sewer system, the greatest test that we saw it run through recently, I know in the 90s they had an event, but in 2019 in April, we had a huge flooding event, and we saw a record amount of flow come through that facility. We saw roughly 18 million gallons come through it, and it's a facility that's rated for a peak at 12 million, so it was barely handling it. But surprisingly, we did not violate a single parameter of our permit. So the facility's built really well, it's built out. We have at least 25 years capacity built into this facility to be able to effectively remove contaminants. But when we do have those storm surge events, there's no way any facility can continue to meet that demand if that was the amount of water they were experiencing for an extended period. But in 2023, the 722 million gallons, we saw that we had a very wet June, primarily a wet spring, and so we saw a little increased flow. Went down 9% into 2023, definitely a drier year, and so you see that impact of seeing less flow, seeing a smaller peak event of only 6 million gallons for that day. To start it off, in the treatment train, we're starting on the east of the facility and working our way west. You have preliminary treatment, and this is really just the first line of defense to the wastewater treatment process. These are called perforated plate screens. They just have thousands of holes across them. They're 6 millimeters in diameter, and they will allow anything 6 millimeters and smaller to pass through, and anything larger than that will get stuck on the face of this screen. As the screen keeps seeing organic and inorganic material coming to it, it will plug itself off just due to the debris blocking the holes. When it does rise up, there's a transducer to measure the elevation on the front versus the back. When the downstream elevation exceeds 18 inches, then the screen says I need to turn on to get new area exposed to the water. And so it will block off all material on the face of these screens. And when it does that, it starts circulating it. It has rake, so it has these teeth to grip everything. And it goes up and over, and then we introduce our first initial blast of recycled water, which is into this screen. And to use high pressure to clean it and then brush it. And so we're cleaning the screen with an automated brush system and high pressure water bar going through it. And it's dropping it off into this compactor and compacting it, and then using more high pressured water to wash the organic material back into the waste stream. We do want the organic material, so human waste, to get back into the waste stream. That is the food for the microorganisms, so we don't want to completely remove that.
What else would be big enough to, besides human waste?
Yeah, you have like coffee grinds, as far as going through those 6 millimeter diameter. Coffee grinds, little eggshells, small debris like that can make its way through those. And so that waste, we do a pretty good job of getting that organic waste back into the waste stream. Anything inorganic, so you name it, it will stay in there. It won't break down due to the water pressure. The water's only like 110 psi, and so it will stay in there, and it'll keep compacting and go through a chute and go into a dumpster, and that ultimately gets disposed of in the Buttes in Oregon in a lime landfill. And then we also remove the coffee grinds, the eggshells throughout that process as well, through a separate process just downstream of the disintegrate classifier. The next thing, mainly every facility has, we do not use it, however, and there's a really good reason for that. This was a primary clarifier that was built in 1956, and the basic component and the mechanism of how it works is you have water coming into the center column, and it provides a quiescent area for the incoming wastewater to be introduced into. And it allows gravitational settling to take place. So anything with a specific gravity heavier than 1, it's going to allow it to settle out. And then anything that's lighter than that, it'll allow it to float. So fats, oils, and grease will float to the top of these, and then this rake mechanism will consistently spin around, collect all the heavy solids down the bottom, remove them, and then collect all the fats, oils, grease, and then send them off and remove them. There's a big reason why we don't use this, and that's primarily because we have a large exodus of people during the break times for the students. And so this facility, we keep a population of microorganisms in it, and they take quite a while to react to differences in incoming food load. And so we're dealing again with a population of microorganisms. We can't just turn things off in a day, let alone even a month. And so we do try to reduce, and we obviously know when students are leaving, so we really try to accommodate for that load. But we don't need this because this removes that organic strength in the food that's actually coming in. And we have so much capacity in our current system that we really do need it. Every drop of organic waste to continue to come in. It won't always be like that, but for the time being, probably for the next 10 to 15 years, we will still need this offline and not to be used. But it's great for storm surge events. If we do have a storm surge event, we can have the water go into there for us. The next step is just influent pumping. These are 3 Archimedes screw pumps. They create our hydraulic grade of the facility, which is just the highest point. From there, we drop about 12.5 feet from this point down to the exit of the facility, and that way everything can really be gravity from that point on and not necessarily be pumped throughout different processes. Each one of these can pump 6 million gallons. We only had to do that once during 2019. All 3 of them were pumping. And this is the first place in which we measured the flow coming in.
What happened in 2019?
It was a flooding event in
Oh,
April.
okay.
Yeah, we had I think it's April 6th or 7th. It was a massive flooding event. Maybe some houses got touched with the water. So the next step, our pumping station was here, the hydraulic grade line. It comes into here, and this is a quite complicated. If you go out in person, it looks very, very. You're just looking at water, but there's a fascinating process happening, and I don't want to waterboard you to death with it. But I will go into the very basics of it. Is one of the really neat parts about this is we actually complete the nitrogen cycle via these microorganisms, and so you have urea coming in the form of the ammonium ion. And it walks its way through, and this is an anaerobic basin, which means without oxygen. And so we have microorganisms that are starved at a process downstream in a clarification process that we starve them of oxygen and food, and we bring them back to the start to the incoming wastewater. And so at this point, that incoming wastewater has only gone through a screening process and nothing else. So that incoming wastewater is a readily accessible fuel source for these microorganisms. So what they do is they've been starved for about 6 to 8 hours, and they'll make their way into here and start feeding on the incoming waste, and they use it as a fuel source. So they have already picked up nutrients throughout the process. We're reusing them. So they keep the phosphorus molecule on them as a fuel source for storage. They will eventually abandon it if they get too stressed. And so that phosphorus molecule is detectable by doing laboratory analysis when we run tests on it. But what they'll do is they'll come into it with it on them. And right now we'll have really 5 milligrams of phosphorus in here. As they keep consuming waste, they'll say, I don't need this fuel reserve anymore, so I'm going to abandon it, and they will start releasing it and then into this one. And like I said, we want to get rid of phosphorus, but what they're doing is they're abandoning it and putting it back into the water. So it starts spiking our phosphorus concentration as it moves through these processes. These are all 3 the same type of tank. It allows detention time and allows them time to consume fuel, and then they ultimately release the phosphorus. Then as they make their way this way, the ammonium ion that was in here, they start feeding on that. And there's 2 groups of bacteria that convert it into nitrite and then nitrate. And then eventually right here, they turn it back into nitrogen gas. And you can actually see the nitrogen bubbles coming through the water, and then it goes back out into the atmosphere. So it's kind of a fascinating process of how it removes nitrogen in the water. So that's a great one to remove as well, because obviously that creates eutrophication in addition to phosphorus. Then as the microorganisms make their way through here, it's a lot of water, it takes a lot of time. They eventually are starving, or they're totally full, but they are really in need of oxygen. So they then make their way into this tank. And when they make their way into this tank, they start having everything they need at this point. They've had food, but they need oxygen. So when they get that oxygen, they start going, okay, great, we're comfortable, we can start taking up phosphorus again. And they'll do what's called a luxury phosphorus uptake in this entire aeration basin, which is just 100 horsepower turbines that are in the water that throw the water up into the air, and it creates a elevated level of dissolved oxygen in here to allow them to replicate and thrive. And so they'll consume all nutrients. So we'll have 5 milligrams come in and below 0.1 milligram leaving of phosphorus out of that basin. This is roughly 4 million gallons of wastewater sitting here. Why it's brown is that it's purely the biological microorganism population. So
How long do they live?
we keep them for about 2 to 3 weeks. So they're replicating. One can replicate in 24-hour period anywhere from 1 to 4 million times, and so we have to constantly waste a portion of them as well. Which that's a great question.
How many,
Oh, go ahead.
how many people maintain this system?
Yeah, there is 5 operators, a facility supervisor, and then a laboratory analyst that work on this. And then we run daily tests on this basin because it is incredibly. If you dump something illicit into the system, they would be impacted. And once they die, you can't regrow them. You have to literally seed it with a new population to get them to come back. Yeah.
Does
So
that-
what eventually
sorry.
happens, what eventually happens to the phosphorus?
The phosphorus stays consumed in the microorganism, and then they get removed in the biosolids process. So we turn them into a solid, and then they get applied to the land. So they hold on to that fertilizer component.
Okay.
Yeah, it's bizarre. We have a solid and a liquid leaving the facility, and they live in the solid.
Okay, so then that's used as a fertilizer
Yeah.
eventually?
Correct.
Okay.
Yeah.
So never mind.
Does the second bank of basins in getting rid of nitrogen emit nitrogen oxides into the atmosphere?
That's a great question. I honestly don't know. I do not know if it does or not.
I'm thinking about greenhouse gas emissions, and
Yeah.
I wouldn't know what.
That's a fantastic
Yeah.
question. Yeah, I'll look into that and actually figure out what it does and doesn't do. Yeah, great questions. Anything else on this? I know this is a lot.
Did you say they're all bacteria?
There's a variety of cultures that are living in this system, and there's like 4 groups of real just heavy lifters on the nutrient side of things, but there is just a plethora of bacteria in that.
When they test for things, I'm sorry.
Go
Go
ahead.
ahead.
There are, people, I was thinking about COVID and how they found out that, COVID was here before.
Yeah.
Are you testing in
Yeah, we
this
actually,
system?
the state, I believe they just dropped the funding of that. The University of Idaho had been partnering with us. We've been doing a couple of different agencies, one BioBot, they were doing free testing. But the U of I believe they stopped their testing in May. But since COVID, we have done it. I think we did a presentation in 2020.
So there are other drugs that or something that you're looking for that that can get through this?
That's a great
process?
question. So we're not permitted to look at that, but of course we secrete that, especially pharmaceuticals. We do know that comes out of us, and so they've studied the microorganisms. They react to nicotine, caffeine, anything that gets excreted from us. They actually do react to that, and so we do know that pharmaceuticals exist there. But until really, we get these new permits that address what we call exotic contaminants. They're so costly to remove. We will keep complying with what our permit states and what it requires us to remove. But we have done pilot programs on stuff like that where you do tests for that stuff. But yeah, the original wastewater epidemiology was quite fascinating. Yeah.
Do you have to, through the winter months, do you have to heat anything so things don't freeze up?
No, this is a really warm process. The water lowest it drops to is about 56 degrees. So you'll see a lot of steam coming off of these basins. But it is, the wastewater coming in is quite warm. Yeah, any other questions on this? Awesome, thank you. When I had mentioned phosphorus, some of the figures that we had looked at in 2021, we were able to achieve an all-time historic low of our effluent phosphorus concentration, and it went down to 0.042 milligrams. And then we were able to do some process manipulation, introduce a variety of different chemical mechanisms into our filtration process, and drop that down to 0.023. I don't think we'll ever achieve that low of a figure again. It really gets to a point where it's not cost effective to keep trying to get it lower. We do want to get it as low as we can, but we want to find balance of that. Again, that's substantially lower than our permit value, which is awesome. And then in 2023, we got it down to 0.048, saved a lot of chemical, got a lot of optimized processes in place, and gave ourselves a really great level of assurance that we're not going to violate phosphorus. It can become really costly. The whole reason we upgrade these facilities and get into compliance is because the EPA will fine you, financially. So, and they have the potential to do it on a daily basis. So we want to make sure this number gets really low, and we're really proud of getting it as low as we can possibly get it. And so definitely a ton of work has gone into figuring out how to do that, but that's all done in that basin process. Yeah.
Did those lowered figures have an impact on dissolved oxygen?
Not necessarily. Where it kind of impacted us was our detention time processes and how long we keep them in a selected area. So on the effluent, it didn't necessarily change a whole lot. Or at least we didn't notice a large deviation of what was historically happening. But so not on the base level did we notice any dissolved oxygen increase from having those lower concentrations. It's a great question though. From that basin, we have that brown liquid, if I may, those microorganisms. We have them leave and come to this clarification process. Again, it's just a quiet area. It's just like our primary clarifier, yet these are about 1 million gallons for the capacity. They're 100 feet in diameter. They allow the microorganisms to settle out. If those mixers on this basin were to turn off, they would settle out rapidly, instantaneously. They start settling and compacting down at the bottom. They do that in these clarifiers. So they settle out to the bottom, they end up getting pumped down here and returned. So these are the ones that were starving. They get returned back to the start of the process to help us consume the waste. And then throughout the day, a portion of them start to get removed to holding tanks to then become into the solids. So we turn them into solids at that point. So they will stay in here for hours. It depends on flow. It's really based off of hydraulics. They'll stay in here, they have no oxygen, very low oxygen, and no new food source. So they're very eager to start the process over again. And then a component of them get removed and wasted out, and that is how we maintain our population, our poundage of population in the system is through these tanks. Following that, we in 2010, when we completed another upgrade, it was about a $10 million upgrade, we did a tertiary filtration system. This is a continuous outflow system. I didn't take a picture of it just because it literally looks like we're looking at nothing. But the CAD drawing of it breaks it down a lot better. But it introduces the water from the very bottom level of these media filters. It's just a very coarse sand, and we introduce aluminum sulfate, and it binds to the colloidal solid, the phosphorus molecule in the water, and then it starts getting attached to the sand. The sand gets continuously backwashed, and then we remove that dirty water and pump it back to the start of the system to introduce the dirty water back to the start of the wastewater treatment process. And so these do the bulk of the additional refinement of phosphorus removal for us. That was their entire intent, was to keep phosphorus low and what's called nephelometric turbidity units, which is just the clarity of the water. It removes large solids, any particulate in water. So these only run legally, they only need to run from May 15th to October 15th, depending on how the week falls. So they're only running for half the year, and that's when the growing season is. So that's when we need to legally remove the phosphorus. and keep these online. So they are not yet online for this year, but we'll get them up and running soon. Following that, they go through a disinfection process to kill any of the pathogens in the wastewater. So we currently use chlorine gas. It's not the safest, but it is highly effective. The plan is to wean off of that and go to ultraviolet disinfection, which will, one, is substantially safer because chlorine gas is, we have processes in place to utilize it safely, but anything can happen when you are working with these. You're working with them on a vacuum system. It's the safest possible way to do it. And we also have a containment for scrubbing the chlorine if there was a leak in those confined areas. Yeah.
How long before you start the ultraviolet?
That's a great question, yeah. We have that built into our capital budget. We anticipate starting design on it in our next fiscal year for 2025, and then working through design and likely anticipate construction of it in 2026. Following that, this is the solids component. So we have the liquid leaving through that chlorination process, and then we have the solids that we wasted and held them in a tank. They are, at that point, they're about 1% solids, 99% water. So if you take a drop of it, that's kind of the composition of it. We introduce it into what's called a belt filter press. It's a series of increasingly larger diameter rollers. We bring in polymer to bind the microorganisms together, to coagulate them, and then we introduce them across this platform. And so as it goes through, it dewaters itself and catches water and drains it off, and then goes through that series of increasingly tighter rollers and just compresses it and literally just makes what we call a cake. And that is what it looks like. It's just a cake coming perfectly off this. That is just microorganisms, essentially. So they have kept the nitrogen in them, they've kept some of the residual nitrogen, and they've kept the phosphorus, and so they have those fertilizer-like values. And historically, this was just being applied to the land in the liquid format. They just put it in a truck and pump it out onto some farmer's property. And actually, it's still, to this day, a ton of cities, that's how they dispose of it, is via just discharging it onto land. You obviously have to get permitting for that, but that is still an acceptable practice. Probably won't be for very long, but that is still present day what happens in some places. But we get it off this and then put it in to trucks. We haul 2 truckloads a day, about 9 to 12 yards of this on a daily basis, Monday through Friday, to Inland North Waste, and Inland North Waste takes it and turns it into a Class A compost. And that has its own permit as well, and so we have to comply with the composting requirements as they sit today. And so that's something where there's the exotic contaminant component coming into play. By the end of this year, EPA's anticipated announcing some of the exotic contaminants that they'll be looking for and looking at putting some thresholds on what can legally be applied to the land. Things like PFAS and pharmaceuticals and all that kind of stuff.
So where is this compost?
This compost is at Inland North Waste, just outside of town on East End. As you're headed to Troy, they have this composting facility, and then they also have one down in Lewiston.
And you can purchase it there?
It's free, yeah, it's actually free. So you can go and grab a truckload a day if you're a Latah County resident. There's products sold in the store called Morganite. That's at Home Depot. I see it at Home Depot all the time. It stands for Milwaukee Organic Nitrogen, and that's from the Milwaukee wastewater treatment plant. And it's the same thing. It's biosolids. They're incinerating it, and so it has no pathogens at that point. Heating it up to 1600 degrees and then pelletizing it, and it's just in a bag. And it's really great because you can actually over-apply it in an area, and it doesn't burn your grass like normal fertilizer does. It releases so slowly that there's all kinds of stories on how great this product is for lawn care. But yeah, that's where we have that process. That process is completed out at Inland North Waste, and we produce about 700 dry tons a year.
And where is that facility?
It's as you're heading to Troy. It's the landfill, or not the landfill, the transfer station that was previously LSI.
And you can just go pick it up?
Yeah, they just have it in bulk out there, and you can bring your truck or vehicle, and they'll put it in.
You called it Class A? What does that mean?
Class A is just a threshold of treatment. It has to have a reduction in its metals concentration. So we analyzed 14 different heavy metals, and then it also has to have a lower classification for salmonella growth. And so it's to just deem it so that it's not going to get people sick. And then it has to have a low vector attraction rate so that animals or different agents can track it. So it's got this vector reduction attraction. So that just means it has to get heated up to a level above, I think it's about 148 degrees for like a 10-day period. So you have to create a really good compost product. And they mix that with an amendment, and so they trommel it together, and then you get a pretty good compost. The disclaimer on that, it does have the potential to have chlorpyrrolate in it, which is a broadleaf herbicide. And so we don't necessarily control that. That is in the amendment that gets mixed with the biosolids. And so there is always the potential of that. So we don't recommend putting it on crops that you're going to eat or that you really hope would live 100%. So it's got a very low amount of it. We do track that number. There is no legal requirement of us having to track that number, but we do track that number in the biosolids. Yeah. Just to touch on some of the upcoming capital projects that we have, we do have about $45 million of potential projects on the 10 to 15-year horizon. Our capital budget currently is sitting very nicely. We have roughly $17 million in funding right now, but of course we have projects lined up to utilize that. The one that's on our heels right now is the IPS pumps, these large Archimedes screw pumps. Plan on replacing those. We're working with a consultant right now to get those replaced and installed next summer. And we are then going to have to do some treatment upgrades on this basin to increase our capacity for the mixers, just larger horsepower motors to be able to accommodate the 1.7% increase that we will potentially see each year. And then we'll do the UV ultraviolet disinfection project and continue to really just maintain the facility with effluent filtration upgrades and potentially a temperature compliant alternative that we have coming up. One thing to note, we did receive the Idaho Conservation League Gold Star, which just means we had no violations for a few years in a row, which is really great. It's definitely hard. It takes a lot of work to make sure we're doing everything appropriately. These facilities are very touchy, and we also had no violations in 2023. So just definitely a testament to the operations team that runs that facility. We are in good hands out there. So it's really, really good to know. So getting into, did anybody have any questions on that? I'm just going to briefly touch for about 10 minutes on the reuse system. All right.
Yeah. On those Archimedes pump,
Yeah.
increasing the pump size, you always look for energy efficiency and the most effective use of these, right?
Yeah, absolutely. Those are, and what's really neat is, or what we've been assured of is, those are probably the most efficient way to move water. They're actually a relatively small motor for the size and the capacity at which they can pump, which is really neat. And so we are actually replacing them as in kind. So we're going to go with the same slightly larger 6.4 million gallon capacity on each of those, and they are unbelievably efficient at moving water, which is really nice. Other alternative is utilizing submersible type pumps. But generally it requires a large variance of motor horsepower to be able to control that potential variance in flow. So these instead run at a consistent rate in RPM regardless, which is really neat.
And you anticipated the UV treatment coming up. Is there anything in the capital budget for ozone or anything like that?
No, yeah, so we did a disinfection study. You may have been mayor during that, I'm not sure. But we did a disinfection study looking at the different disinfection alternatives that are available. And we settled upon UV. One, it is becoming increasingly more popular in the industry. So the accessibility to actually having those components and the effectiveness of it is remarkable on those UV systems. And so the redundancy, the the redundancy features, the safety features of it is really what guided us towards wanting to look at an ultraviolet system. We'll get into that, study it a little bit more, and then, but I'm pretty confident we'll go with an ultraviolet system. But yeah, I did look at quite a few alternatives and ended up landing upon UV.
And the last question I've been saving
Yeah.
up for you is that whether the aluminum sulfate residue causes some effects on the sludge, so that you get, crusting and impermeability
Yeah,
and things
yeah.
with the compost and stuff. Is there enough residue in there for any problems?
It hasn't not necessarily on the solids component. We don't have much of an issue there. Where we do have an issue is on any metal that it contacts. It's incredibly corrosive. So when we do have large dosages that don't get removed in backwash, the filter does a remarkable job at backwashing to hopefully get that residual value down. But where we do notice it is in any contact of metal, not necessarily in the solids component. Great question. So history of the reuse system. The city approved development of the effluent reuse system with the U of I in 1976, and there was an interagency agreement executed in 1977. Since then, we've reused roughly 3.5 billion. I say roughly just because we don't necessarily, I don't really trust flow meters back then. It's hard to say the accuracy. Even today's most accurate flow meters they can have a 6% variance, so that gets pretty large pretty fast. But for the most part, it's a ton of water that has been recycled since 1977. And the goals, what they recognized the necessity of it was conservation of the underground water supply being the first, and reduction of electrical energy. It's very costly to pump water from 300 to 600 feet from the ground. Also the reduction of fertilizer requirements, because that water has some of that phosphorus in it, so that does help with the fertilizer component, and then creation of an uninterrupted source for their irrigation supply. And how this works, it's actually really straightforward. And we run through our treatment process. Depending on the flow that we're seeing, it can take a drop of water about 24 hours to get through the facility. And it'll make its way through an ending diversion box right here. And we send them water that has been chlorinated. They have a 244-day period at which they can utilize this water, so pretty much from March to October. And we send them chlorinated water. We also have to send them filtered water. We have to be below 2 NTUs, nephelometric turbidity units, for them to be able to take that water. And so it comes out chlorinated and just moves via gravity over to their holding tank. And currently they have a covered holding tank. They had an open exposed lagoon. They were off-gassing chlorine, which wasn't effective. It was allowing regrowth of bacteria in it. And so they utilize a Class B reuse effluent. So this water flows via gravity. They control a gate set point through our SCADA software system that just tells them to modulate open and send them some of the water. And so we send them the water via gravity and introduce it into their tank. They then rechlorinate it to get it to a Class B standard, which just means that there's a reduced pathogen. They reduce the pathogens with the disinfection. And then they have a pump station over here that then pumps it into the system. And currently, they pump from here. When they started this in 1977, they had an initial capital investment, I think at that time, of like $390,000, pretty low to today's standards, but they had a 40-year bond on it. So I think their all-in cost was somewhere around $2 million for this reuse system. I'm not sure what that is in present-day dollars, but what they were able to get with that was a distribution system of some 8-inch pipe, 6-inch pipe, all the way down 4-inch and 2-inch pipe. But it does irrigate roughly 85% of their campus. Obviously, if you play the U of I golf course, there's 2 ponds out there. They can hold a little north of 2 million gallons of recycled water in them. And that's their primary mode of distributing that water through those systems. And so those are able to hold the water for them. One thing to note is we can't give them every drop of water that we are producing, even though technically they could probably take it. We do have to create a residual value of water leaving our facility to ensure that some of our dechlorination equipment stays primed and ready to be utilized in the event that they tell us that they can't take water. And so we can't have any chlorine leaving our facility into the receiving body of water. So we do keep it's about 200,000 gallons of water per day, the potential to keep it flowing over that gate and into the system. So that way we can, in our current means of disinfection, so that we can remove the chlorine in the downstream process. But that's kind of the outlay of where they're utilizing the reused water. The advantages of it are the demand reduction. Obviously, it reduces the local demand on our aquifer. And the nutrient benefit that I had mentioned for the fertilizer, and with us, it's a temperature, the temperature TMDL reduces our effluent temperature by essentially what the load is that we're distributing each day. It's a variety of the creek's flow rate, our flow rate, the temperature of the creek, and the temperature of our effluent. And there is a sliding scale on how we come in compliance with that. But the more water they take, it helps our discharge effluent from it. And then sustainability, good stewardship between the university and the city's resources. Of course, there are disadvantages. The regulation component of it, there's tighter regulations on reused water than versus just potable water. If they were just to use aquifer water, they could do it at any time. They wouldn't have to worry about putting that on the ground. Application depends upon the class of the system and having buffer zones. The additional costs, you have another infrastructure component built in. So you have a new distribution system to run water through, and replacing pipe currently is unbelievably expensive. So if they did have to replace some of that, I'm sure they will eventually, but it will be expensive. And then licensing, training for personnel. You need a new license in the state to operate that system, so somebody has to have a reuse license to be able to do so. And this is ran by the University of Idaho, well, technically McKinstry. They have operators that operate this system. We just send them the water to do so. Yeah.
Over the years, there have been discussions of having satellite treatment facilities.
Yeah.
And I'm thinking about the lift stations going in
Yeah.
and new development happening. If the University of Idaho effectively has or questionably has water rights to the total amount of effluent, or maybe not, we don't know, then could there be reclamation that takes place before it gets to the main wastewater treatment or water reclamation facility?
You're absolutely right about that. That was studied under our 2012 adopted comp plan for the sewer system, was the potential of satellite treatment facilities. They do make these package-like plants. They're membrane plants, where everybody's heard of reverse osmosis, very similar to that. Very small footprint. They are costly. They're somewhere around the $10 to $12 million mark present day. But what you are referencing is, in the instance where it's more effective to not pump that water back over to this facility and keep expanding this facility, you treat that just kind of regionally throughout the community. You do need additional permits for that, so we would need new permits for that facility. So that's one of it's not necessarily a hurdle, but it would take obviously a substantial amount of time and then I guess the study aspect of it. But it is the cost. I think it is a little. It's hard to say. It's a little. At least the recommendation of the comp plan had recommended they're costly, and they do become. An option, but I think at this point it's not the most viable option for us to pursue and put our effort into having satellite facilities at this point. Great question. Was there another component to that question?
Oh no, I'll just keep bubbling along with that one though.
Yeah.
It's been on my mind a while.
Yeah, that's a great one. Just the major concerns, the public health concern, the possibility of causing people to become ill. What I know from experience of at least this recycled effluent, they do have, since it's a Class B effluent, they have to reduce it down to 2.2 total coliform counts in each sample. That's the maximum that they can have. They have historically been at 0. We've never seen them hit. We do their sampling for them to test for that compliance, and we haven't seen anything. So in the same ground, if we're taking a water sample, we're having 0 total coliform units in E. coli on that sample. So not to say it's drinking water by any means, but it's not necessarily has has the pathogen concern in it, but it can, and they can have 2.2 in their sample. And so it's always there, but the action for that is kind of actively irrigate during periods of non-use. And so that's what they do. They do irrigate the system in non-use hours. The pathogens I had mentioned, the nitrates and sulfates, those primarily predominantly found in more industrial applications, so we don't necessarily have that same concern, but that is a concern in some cities. Surface water pollution, potentially contributing to surface water pollution. The action to that is kind of controlling runoff, not overwatering. Their permit is very clear about they don't want to be super saturating areas to allow that runoff to take place. And then just the public perception of the whole thing, the ick factor that is present with it. Some of the largest communities in the country are using fully recycled water, Orange County, California being one of them, but everybody out there has to have some sort of supplemented water supply for use in their region, and so they utilize full reuse throughout their system. They have supplement, they directly discharge it back into their aquifer, they supplement with the Colorado River, but then reuse their wastewater as well on an annual basis.
Since there's a problem with water in the future and water use in this area, is it possible ever to do that same process here?
Yeah, we can. So we do have a city representative, Tyler Palmer. He's on our PVAC committee, so he's been PVAC helped identify I think it was roughly 4 or 5 alternatives. They've narrowed it down a couple times to what the most strategic and just, I guess, achievable strategy would be. I know in there early on it did reference utilizing recycled water and maybe discharging it into the aquifer. Communities have done that, and some of them have had great success with it, and others have not had near the rechargeability that they had hoped for. They were hoping to take all wastewater effluent and put it into the ground, and sometimes the aquifer couldn't do that. They don't fully know how these aquifers react in every facet, and so there's also the downside of removing all water from the creek. During summer we are for the most part we are the creek downstream of us. We create flow that moves down there, so that would be a substantial amount of water lost in that area. Is it possible? I think it certainly is. Do I think it's going to happen? I don't think so. For the most part, I think we're reusing. I was going to go over the total impact figure, but we reuse roughly 20% of the overall wastewater that comes into the facility, gets recycled. 20% of that is recycled. We do about 100. Last year we did 103 million gallons to the University of Idaho, and then we do roughly 30 million gallons at the facility. So we use that on our system processes, some of the equipment, the plant cleaning, and then our irrigation, our green space at the facility. We utilize that water as well. So we do utilize a fair amount of it, but as far as the water alternative goes, I know that they're working towards a selection of what's the most effective alternative, but I know there is nothing written in stone at this moment with what will be the most strategic way to move forward. That is all I have for you guys. Do you guys have any questions?
I don't know if we have time.
Yeah.
Is there any thought to using this water for human use, say for showers, and for non-consumed water, and then a second system for drinking water?
Yeah, it's a great question. That's been the some communities, as they laid them out, like Meridian, they utilize it for all their irrigation purposes. If a city has the ability to expand early on and have that forethought in what they wanted to do, it's really easy to get the pipe in the ground at that time. Going around where we're currently at, it would be astronomical in cost to get that into the ground, and so it comes down to the cost. It would be amazing to do, and cities are doing that for stuff like irrigation. But
what about in our new developments?
It would still require us to then get that water from the west end all the way to the east end. And so it seemed, in theory, it would be incredible. But the actual practical application of it is just really costly. Yeah.
Do you think it would be necessary to do that, or I mean, just from your own opinion, the science of it, do you think that would be unnecessary, that we could, I mean, do we lose anything if we move to Orange County? Is there something to really be afraid of going that direction?
I don't think so. What they're doing, I mean, their treatment process is ultimate. It's the best we have available. It's reverse osmosis. They have PFAS removal stations for that emerging contaminant. But the reverse osmosis component for treatment literally strips everything out of the water, and they have to reintroduce minerals back into it because it's a tight process. And so it would be amazing. It would be a great way to go. I don't think to the science that we have today. I don't think it's necessarily going to be anything that would be detrimental to people. But large cities have invested a fair amount into doing that. Same thing like the space station. They reuse the water just in that same fashion, and consume that. I don't know. I guess it's time to tell. Thank you, everybody.
Thank you.